We're back. This is Unit 7, Section 1, page 4. Let's see if we can get through pages 4 and 5 today. Okay, we are at properties of radicals. We have the quotient rule. Notice how you can go back and forth between having the fraction under one radical or having two radicals, one on the numerator and the other one in the denominator. This is for simplifying purposes. But in the end, you will not be able to leave your answer with the radical in the denominator, but we'll worry about it when we get there. So you can go back and forth between these two different settings, but there's not a best one. It's going to depend which one you can simplify or it's best for you. Product rule, you can go back and forth between having two separate radicals versus both of them under one. And it looks like this. So if I have square root of 5 times square root of 7, you can just multiply and you get square root of 35. Now this one, you can split up like you would here. So square root of 64 over square root of 121, they're both perfect squares. You can just easily simplify that down to 8 over 11. And this is the final answer. Now here you have cube root of t over 125. When you split that up in two roots, I know from the get-go that 125 is a perfect cube. So you cube root 125 to get 5, and there's nothing you can do to simplify that t right there under the radical. So final answer will be just cube root of t over 5 because I simplified that right there. Here I'm going from square root of 7 times square root of 11, giving me just square root of 77, and I cannot simplify that square root any further. Now this one, there's a whole bunch of things going on at the same time. Notice how I have the product rule right here on top and the quotient rule right here because it's a fraction. I can divide to begin with. Why and how? Well, I can go from this format. I'm going to add a side note over here. So it's like I'm only looking at cube root of 6 over cube root of 2, and then I can bring them together under one root, 6 over 2, and that's where 6 divided by 2 is just 3. That's where this came from. Okay, that was my thought process to go from this whole thing to this. Okay, that's where that came from. So, and then we're down to only product rule that I just 3 times 72, that's 216. 216, again, is a perfect cube. So you cube root 216 and you get 6. And I know that 216 is a perfect cube because it's the same thing as 6 cubed. Don't know. And because the index and the exponents are the same, I was able to simplify that. Here's the same thing. I went from 2 radicals down to 1 because 32, it was like this. 32 over 2, that's 16. And then simply square root of 16 is just 4. We multiplied the radicands over here. 6 times 8 is 48. And then I split that up to where I could simplify that 2 to the 4th power. 2 to the 4th power is 16. 16 times 3 is 48. That's where this came from. And, with practice, you will get the hang of it and you will be able to identify more and more those perfect cubes and the fourths right there. So 4th root of 2 to the 4th power, I can simplify down to 2 because the exponent and the index are the same. And then I cannot do anything with that 4th root of 3 right there. I cannot simplify that. There's a side note on the next one. Notice how we're taking the cube root of a negative number. You're not going to have an imaginary here because this is a cube root. That's an odd root. The index is odd. So when you take the cube root of -1, you get -1. So this -1 is right there part of your answer. Okay? And then cube root of 27 is 3 because 27 is a perfect cube. 3 times 3 times 3 is 27. And same thing with 64. 64 is a perfect cube. 4 times 4 times 4 is 64. Okay, simplified, easy. Now, when you end up with a radical in the denominator, you need to get rid of the radical in the denominator by doing what we call rationalizing the denominator. Some of you might remember this from Algebra 1. Some of you may not, and it's okay because we have a simple. This is the simple that you probably remember. That's when you multiply numerator and denominator by whatever radical you have. And in this unit, we're only doing square roots. We're not going into cube root or anything. So you multiply numerator and denominator by the square root, and then you're going to multiply across. So 12 is 12 right there. 3 times 2, you have that 6 right there. Since it's under the root, it remains under the root. Square root of 2 times square root of 2 is square root of 4. And then square root of 4 is a perfect square. You get 2. So now there's nothing I could do on this step to simplify the numerator. So now the last thing I need to do is simplify that fraction. 12 over 2 is just 6. And then the square root of 6 doesn't go anywhere, it doesn't simplify. Now, the next one is a little more complex, to where you have a binomial here in the denominator. And one of the terms in the binomial is a radical, it's a square root. So you have to multiply by the conjugate. What is it? The conjugate is when you keep those two terms and then you just switch the sign right there in the middle. And I'm going to show you how it works and why it works. The whole process is, the goal is to get rid of the radical in the denominator. And this right here will make that happen. So if I'm multiplying this binomial by this binomial here, here's the box. If you want to do foil, but I want to do the box so I can show you how and why it works. So I have the 2 plus square root of 3, 2 minus square root of 3. Multiply, you get that. Multiply, you get 2 square root of 3. And then here you multiply, you get negative 2 square root of 3. And then you multiply here, you get negative square root of 9. Perfect. Because square root of 9 is a perfect square, I got this negative 3 right there. Now, 2 square root of 3 minus 2 square root of 3, they add up to 0. And that's the goal. They go bye-bye. No more. That's 0 square root of 3. So mission accomplished. I don't have a radical in the denominator anymore. So at this point, I only have 4 minus 3 that I got from over here. That simplifies down to 1. Easy money. And then here, I still have the leftover, and I have to distribute that 7. So 7 times 2 minus square root of 3. And then you distribute, you have 14 minus 7 square root of 3. Okay, just doing more. So I go from 2 radicals down to 1 radical. Simplify 6 over 3 is just 2 and square root of 2. Here, first I split that up in 2 radicals, square root of 21 over square root of 5. Then I have to rationalize the denominator by multiplying numerator and denominator both by square root of 5. That's why it's in orange. Then I multiply across. 21 times 5 is 105. 5 times 5 is 25. And then I got that perfect square that I was looking for the denominator. Square root of 25 is 5. And there's nothing I can do to simplify this square root of 105 right there. I have in the numerator. But it doesn't matter. I can have the radical or the square root in the numerator, and it's fine. However, you always need to check if you can simplify the radical, you must simplify the radical. You cannot leave your answer, for example, as the square root of 48. You have to simplify that. Do not leave it like that. Okay, this one, we're rationalizing the denominator by multiplying by the conjugate. So square root of 2 minus 7. And then you do the box. Notice how when you're combining like terms, the radical will go away, or the radical will add up to 0, hopefully. Square root of 2 times square root of 2 is square root of 4. Nice, because this is the perfect square right there. And then you have 7 times negative 7 is negative 49. 2 minus 49 is negative 47. That's where that 2 came from right there, from the square root of 4. And then here, we're going to just leave it like this, and then you're going to distribute. 3 times square root of 2 is 3 square root of 2. 3 times negative 7 is negative 21. And then you just double check to make sure that you cannot simplify this fraction any further. Multiply by the conjugate. Square root of 5 minus 4. We're going to do the box right there for the denominator. Square root of 5 plus 4, square root of 5 minus 4. Multiply, you got a perfect square. That's good. You combine like terms, you got 0, square root of 5. And then you have that negative 16 right there. So 5 minus 16, you got that negative 11 right there. And then you just need to multiply across. 2 times square root of 5 is square root of 10. Square root of 2 times negative 4 is negative 4 square root of 2. And you cannot add them together. You cannot even simplify any further. You can only add if the radicands are the same. Here you got a perfect square in the numerator, but the denominator is not. So you have to rationalize the denominator by multiplying by a square root of 17, numerator and denominator. That will give you the perfect square. So just regular 17 in the numerator. Square root of 100 is 10, perfect. And then square root of 17, there's nothing you can do. Multiply by the conjugate. So 1 minus square root of 5. So that changes it to 1 plus square root of 5. Here's the box. Multiply 1 minus square root of 5, 1 plus square root of 5. The diagonals here add up to 0. That's nice. And then here you have square root of 5 times square root of 5. That's a perfect square right there. So you have 1 and square root of 25 is 5. Bam. Put them together, negative 4. Distribute. You got 4 plus 4 square root of 5 because you multiplied that right there. And then notice how here you need to simplify the fraction. You're going to divide this one by 4, this one by 4, and also this one by 4. And then you are able to simplify. You have negative 1 minus square root of 5. Perfect. I think I can keep going. Okay, adding and subtracting radicals. That's what I just quickly mentioned on this example right here. I can simplify those because they have the same index and the same radicand. Okay, I can add them together. I could combine these guys because they have the same radicand. Remember, the radicand is the number in front under the radical and the same index. So I could simplify that. But this one, I have two different ones. I have cube root of 2 that I cannot put together with square root of 3. The radicands are different, the index are different, so I can't put them together. Okay. This one, I need to check first. They have the same radicand. Nice. So I can definitely combine. So 5 plus 2 is 7. Square root of 25 is 5. Simplify. 7 times 5 is 35. Done. That easy. Check first. They have the same radicand, the same index. So 8 minus 4 is 4. Square root of 5. It's like combining like terms. And this would act like your variable. They have to be exactly the same. Okay, they both have cube root of 64, so I can add them together. So 3 plus 7 is 10, cube root of 64. At this point, you guys agree with me that 64 is a common known perfect cube. And cube root of 64 is 4, because it's 4 times 4 times 4 is 64. So simplify that, you get 4. 10 times 4 is 40. This guy, I can only combine part of it, I can only combine this one with this one, because this square root of 5 is different than the square root of 3 that I have. So I can only put these guys together. So -2 minus 1 is -3, square root of 3. And then you're going to leave this guy alone because it doesn't go with anybody. Same thing right there. I will put these guys together. So 2 plus 3 is 5. Square root of 9 is 3. This doesn't go together with anything, so you just keep on carrying it down, and it's going to be part of your answer. So 5 times 3 is 15, and there's nothing I can do to simplify. And then the last one on this page, and then I'm going to stop the video right here, is they're both square root of 6. They both have the same index. They both have the same radicand. Perfect. So 2 minus 2 is 0. So it's just 0. You can write 0 square root of 6, but it just looks funny. So just 0. Goodbye.